1966 to 1967. He was Associate Dean of School of Design at CalArts from 1969 to 1972. He's the author of Structures in Nature as a Strategy for Design, and Polyhedra Primer, and Experiments in Form. I think he's gone through a very interesting process in his development. He's always been a very, as I can ascertain, a very practical person, and likes to get things built. And he started at a scale that he could implement his ideas because of his interest in polyhedra and so on. And he started with toys. And as I look at it, he built larger toys and larger toys, and now he's building adult toys. And he calls them space frames, and they're used throughout the country now. And he's got projects also in other parts of the world. Probably his most noteworthy accomplishment to date, he's been a consultant on the Green Machine. That is yet to come. I had a meeting with Mayor Bradley today on the Green Machine. He'd never even heard of it. Another thing he's noteworthy for is he hires SCI-Arc students. He must have had 6 or 7 run through his office there. He's had 4 that have worked with me. And will you welcome Peter Pearce? Thank you.
Thanks, Glenn. I can't see that close. Can you hear me? Thank you, Glenn. That was all true. Okay, I'm a little shell-shocked this evening, and I guess it's because the company that I attempt to run has grown incredibly, I mean unbelievably, in the last year. A year ago, February, it had 7 employees, and it now has 100. And I'm not really quite sure what to make of that, but it relates to, it's a very strange experience because it relates to an interest that I began pursuing about 18 years ago. And I think had I known, and in fact that interest really was the developed out of asking what seemed to be a very innocent couple of questions having to do with certain design problems that interested me. And I think had I known what the implications were of asking those questions, I would have found other questions to ask. Because although it's been an interesting trip, it's hair-raising most of the time. I think let's just go right to the slides. I have a feeling that I'm standing in the wrong place, but if we turn the slides on, maybe I can decide that. And can that be focused? More? Better? Okay. The question that I was interested in 18 years ago, I didn't really understand it very well, had something to do with the idea of trying to develop systems for creating structures, architectural structures that were intended to be mass-produced, or that is made out of mass-produced components. And the classic argument in those days was, when you talk to architects, was that, well, you really shouldn't use, I mean, even 18 years ago, this was still a serious kind of response. You shouldn't use mass production to make buildings, because the requirement of mass production was standardized components, and if you use standardized components, it followed that the resulting architecture would all be standardized. And since I wasn't trained as an architect, I didn't believe that, and so it didn't seem like a logical conclusion to me. So I got interested in the question: well, if you the question, could you design standardized parts that could be made in a factory and reproduced and take all of the advantages of that kind of system that could be recombined in as many ways as possible so that you had the possibility of infinite diversity generated out of standardized systems? And I started fooling around with that question and that problem and was getting nowhere fast, and I felt that what I really needed was a theoretical framework for dealing with that issue, and that led to really kind of looking at natural structures, particularly crystals and other things, and that subject is dealt with at some length in my book, Structure, Nature, and Strategy of Design. In any case, what you're looking at here, obviously, is a bunch of snow crystals, 37 different ones. And that became kind of an archetypal model of this notion, which I came to call minimum inventory, maximum diversity systems. If you think of the molecular structure as a kit of parts, as a building system, it has certain geometric constraints, physical and chemical constraints, that cause all snow crystals to become six-sided. They have the symmetry of a regular hexagon, yet within that constraint there is an infinite number. And the way a snow crystal is generated is that it's generated as an interaction of the intrinsic properties of the system. All systems, even if you're using 2x4 sticks, they all have intrinsic properties which tend to guide you in certain directions. All systems have intrinsic properties, just as the molecular structure of the crystal does, interacts with the environment, which is temperature, wind, velocity, whatever it is. And the snow crystal is a perfect synthesis of that interaction of forces. And what was very interesting, and what you start to learn when you study natural structures, is that their behavior is inevitably and invariably a minimum energy response. Each snow crystal represents an arrangement of least energy with respect to all these forces playing. So that became an important corollary issue. Where's the thing here? So in effect, the form of the snow crystal became a diagram of forces, which became a kind of compelling thing. If you hire an engineer to store the greatest amount of honey with the least amount of beeswax, this is the solution to that problem because it minimizes surface relative to volume. It takes the bees less time. The bees are obeying, as do all natural structures, what might be called the law of cosmic laziness, which is that nature is, sort of doing it the easy way. A more complex manifestation of this notion is this three-dimensional soap bubble, in which, again, surface to volume is minimized. Not only that, it's a highly ordered structural pattern, even though when you look at that, that's a random froth of bubbles that looks totally sort of mixed up and non-uniform. If you look at the intersections, the vertices or the corners where the edges meet, you'll see that there's no exception to the rule that four edges meet at each point. And they not only meet at each point, they meet in equal angles. Every angle around each point is 109 degrees 28 minutes, which is the central angle of the tetrahedron. The other thing is that on each edge, three faces meet at 120 degree angles, and that happens to be the interior angle of the bee cell. And so the curvatures that you see are accommodating those angles. In any event, it ends up being the soap bubble, a model or a subfroth of all cellular froth and natural structures. The more fluid the interface, the more exactly, literally, it's like a soap bubble. So animal cells look that way, metal grains look that way. This is about a 2 million times enlargement of a platinum structure in which each white dot is a single atom, and the beautiful patterns you see there is really the consequences of a very dense packing of atoms, which ends up being a very stable structure and is characteristic of many metal structures. The relationship between say the bee cell model or the soap bubble model and the dense packing or so-called cluster packing of atoms is that they're both organized on a triangulated grid, which is in fact the way they relate to space-frame structures. The only intrinsically stable, as you probably all must know, geometry available in the universe is systems made out of triangulated arrangements. So the surface to volume optimization is inadvertently related, or not inadvertently. A simple experiment that you can do, kind of kindergarten level experiment. If you built a cube, which is the overwhelming spatial bias in architecture and design, and treat that as a load-supporting structure. It's made out of 12 members. You load it until it collapses. You get characteristic moment-induced S-curve distortions in the members. If you took those same 12 members and built them into this form, which is called an octahedron, it curiously takes twice as much load to collapse that structure. The members are the same diameter, same cross-section area, and same length. That is the essential principle of the space frame. space structure. What I then got involved with, this is still some time ago, was since from the point of view of generating variations on a theme, generating diversity out of standardized parts, orthogonal geometry wasn't the most promising, and since from a structural point of view it wasn't the most promising, it seemed useful to look at every possible geometric system. And so that's kind of literally what I did. I spent a lot of time studying crystallography and repeating networks. And this is a model of it's kind of an integration of about 100 different uniform networks in one model, which became a kind of universal structure, which if extended infinitely, you could treat any given structure as a subsystem of that. But the main point of this is that it led to a modeling system which, kind of an ultimate tinker toy, which you see here. Some of you may have seen this, which is consisting of something called the universal node, which is a star-like object with 26 spokes of differentiated cross-section, square, triangle, and rectangle, and matching branches. And those really are symmetry elements. What this is a physical embodiment of the principles of symmetry that govern the way parts fit in space. And I want to assure you that it is, in fact, principles of symmetry that govern the way parts fit in space. Parts don't fit arbitrarily. You can't occupy the same space at the same time with the same piece of same entity. And so what this does is the shape coding preserves the orientation of the node. The practical significance of it is, so if you start plugging nodes into branches, in this case all rectangles which curiously build equilateral triangle space, you don't, the node, the spatial system, the modeling system, I should say, has a very high spatial IQ, so that the user does not need to have a high spatial IQ. He can be completely unfamiliar or ignorant of these systems. As he starts to play with it, the mechanical feedback system and the modeling system teaches you as you go. And we've had 6-year-old kids, 7-year-old kids doing extraordinary things, and even adults occasionally. So it becomes, this was marketed as a toy 10 years ago when we started the company, which it failed dismally. All of our, I guess I should digress a minute and comment on some of that. The reason, well, let me finish this sequence and then I'll comment on it. I'll digress. Anyway, that's all rectangles. This is all squares. So we haven't thrown the cube out. We're just trying to define that in a broader perspective. The cube is obviously a useful structure for many reasons. And this is a model which combines the rectangular and triangular branches with a very dense triangulated structure, which in fact happens to be the model of that platinum structure that I showed you earlier in the micrograph. One thing that I should mention, I think, to put this in the proper context, is that I was trained as a product designer and in fact spent some years working in that area. But as I got into this other stuff, I couldn't find any clients to pay me or hire me to do this. Nobody seemed to want this information. And so I kept sort of struggling with the question of how do I survive? I mean, I could always get a teaching job, which is in fact what I did often, but I always felt the need to verify in the real world these ideas. And but as I said, I couldn't find anybody to hire me. So I ended up deciding that the simplest way to do this, the biggest mistake in my life, the simplest way to do this was to start a company that would manufacture some entities that came out of this kind of work. And so I became, with some other people about 10 years ago, a manufacturing organization. And we started by producing these toys which embody these principles, and we made many toys, none of which were successful in the marketplace. And we discovered that we were able to stay in business for many, many years through two mechanisms. One was something called investment, which you could do for a couple of years and then you couldn't get investors anymore. The other thing, which is probably ultimately more significant, was something called debt. We had enough credibility that we could get people to loan us money. We were never profitable, but so what happens is that you end up getting in sort of deep shit, if I can be blunt, from a debt point of view. But you were able to survive, and it seemed like the principle was that if you could hang on long enough and continue to pursue the notion that, at least you were going to test the limits of it, which is about all you can do in life anyway. But what's happening now is that apparently, I think about a year ago I told this to my wife, for the first time in my life, the things I'm interested in seem to be what people want. I don't understand that, but seems to be the case. And as we started in the toys thinking that would be easy, and we would get a lot of sales, and we move up through playground structures and then into large-scale architectural systems, which was always the intention. It's been easier to get the business as we got larger, which you'd think would be backwards from that. The idea was we would sell toys and make a lot of money and have discretionary money to put in R&D to make the larger scale systems. Didn't work that way. In any case, so the point I was making was that we don't do any consulting design except for nice guys like Glenn, which we did on the Green Machine. We do that occasionally, but our main focus is actually as a manufacturing organization and as a product development organization. As part of that effort, we get involved in a lot of projects that require making buildings, and we do a lot of design. We have a lot of architectural design and everything happening there. But it's mostly related to kind of developing the system, refining the system. Every project that we do, and you'll see them in a minute, is kind of a prototype for the next project, and at some point maybe we'll become architects, I don't know. But in any case, back to the slideshow. You sort of go through all this geometry, and it gets pretty damn compelling, and it's interesting and all that stuff, entertaining. But I really was not interested in becoming a sculptor. I wasn't interested in becoming a specialist in mathematical games. I didn't want to be an entertainer. I was really interested in building things out of this stuff. So the question came up, well, what the hell do you do with this? I mean, how does this relate to architecture? And the simplest and humblest, seemingly possible application was in something called space frame, which is by this time, a generic class of structure that, in fact, as you probably most of you know, if you don't, you should know that the first true space frame made out of equilateral triangles in the form of tetrahedrons and octahedrons was built by Alexander Graham Bell in about 1902. Not only as a tetrahedral kite, which we also produced recently, no longer do that, but he built structures, windbreaks and towers and all kinds of things. So since that time, the space frame has emerged as a generic solution to certain problems. But a couple of things I want to emphasize. One is that the space frame is not really what we started. I didn't start the research in 1964 to do space frames. The space frame is kind of a subset of a larger picture, but it happens to be something for which there is a market and it's an acceptable solution to certain problems. I just totally lost my train of thought. Well, I guess the next thing I would say is that from Alexander Graham Bell there were various developments in the history of space frames. Mostly after the Second World War, there were some primitive things happening probably in the 30s, but there was a guy named Robert Laricolet, who was a Frenchman who ended up at the University of Pennsylvania, who died, I guess, about 2 years ago, maybe last year. A very significant person in this area was Conrad Waxman, who in fact died very recently, who was really not an expert in space frames, although that's what a lot of people think, but he in fact did some spectacular proposals in the late 40s, early 50s, using space frames for making large spans, in particular if you don't know his book, The Turning Point of Building, you should find that somewhere and read it. It's not exactly a current book, but it deals with the industrialization of building and that sort of thing. But what Conrad did was he called attention to the connection, the joint, if you will. I mean that literally, not metaphorically, as a central part of the problem of designing these kinds of structures. Bucky Fuller did a few space frames and other people, and now there's a lot of people in Europe that do space frames. And there's a lot of systems available. Some are custom systems and some are factory systems. A lot of people have tried to build space frames out of consulting engineering firms and through architects and so forth, each of which was a custom job. They said, I want to do a space frame, and there was no system that was the right scale or size. So they welded something together or they designed their own joint. And whenever that's been done, the results have been extraordinarily expensive. And so through the years, the reputation evolved that space frames were very expensive to build and that sort of thing. Then there was the emergence of a system called Unistrut, which now is called Moduspan, if you look in Sweet's catalog and so forth, which ended up being the most readily available, economical, off-the-shelf system developed in the U.S. As we sort of looked at this problem and tried to get serious, because we as I said, we weren't looking at just space frames, we were looking at some pretty harebrained, far-out ideas for buildings that depended on these kinds of structures. The question was, what is going to increase the likelihood that somebody's going to want to use this kind of system? And the answer to that question is economic viability. You can't, I mean, if it's going to be reserved for only the, I'm going to eat these words, but if it's going to be reserved only for exotic, high-class projects, then it's not going to become a mainstream kind of technology and have limited use. And the reason I'm going to eat those words is most of the projects we're doing are high-class, elegant projects. But there are more of them than there used to be because, in fact, it is becoming more economically viable. So in any case, what we said is we wanted to develop a, well, first of all, you have to analyze what are the cost parameters of a space frame. There are two primary things, or perhaps three. One is the intrinsic efficiency of the structure, which is the strength to weight characteristics, which determines how much steel or aluminum or whatever you're going to buy. That's one aspect. The other, probably most significant aspect, is in fact the Conrad-Waxman problem, the joint connection. And if you looked at the available systems today, you'd find that the more sophisticated the possibilities were, the more expensive the system became, and there's an incredible disparity. I mean, there's a threefold or fourfold disparity in the off-the-shelf standard systems available, and if you start making your own, you're talking about 5 or 10-fold disparity. I mean, you can go from $7 to $50 a square foot, and to the uninitiated person, that would look like the same system. So we said, what we want to come up with is a solution to this problem. The third thing I didn't mention was the erection cost of these things is also, it's not as significant as the other costs, but it is an element to consider. So we wanted to come up with a solution to the problem of economic viability in which we had a intrinsically more economical system than any known system, and an intrinsically more sophisticated system than any known system. That is, we want to be able to do more than anybody else had done before, but we wanted to do it for less money. And so we started working on the problem of the connection, the node as it commonly known, the node as it is known, something like that. Anyway, so started working on the problem of how do you make an economical node, and went through, this was my hobby when we were producing toys. If I couldn't sleep at night, I'd get out my book and start drawing nodes. But it became, there were many solutions to the problem that were nodes, but none of them seemed to really have the combined properties of low cost and high sophistication. So we kept asking questions about the problem, and finally said, well, what really is the function of the node? And one answer, usually any good question has more than one answer, and one answer to that question was that the function of the node is really to join struts together. And so you say, aha, the problem I'm trying to solve is not to design a node, but to figure out a way to join struts together. And that's not the same problem. And as soon as you ask that question, you get a different answer, which is that you don't need a node. You join one strut directly to the other. And the way you do that is you have a little stamped tab that gets welded to the strut in whatever combination you need, and then you hook one to the other and so forth. And so that's really what we developed. And in fact, it is intrinsically more economical. And but it's also a kind of Pandora's box in the sense that as soon as you get to that point, then there's a whole spectrum of problems associated with it. How do you really make it? How do you optimize the manufacturing? So we have to we're developing a computer-run automatic welding system to make those parts. It's about 6 months behind schedule. It should be running in about a month. It all moves now, but it doesn't weld anything. It's quite bizarre-looking machine. It'll weld any size strut. You get into some extraordinary engineering problems because no engineer that you'll find, I mean, call any engineer in Los Angeles or LA and ask them how this thing works, and they won't be able to tell you. And we have found that we had to set up our own engineering department. We have 3 PhDs who are coming to work every day now, which we just started happening, and working on this problem. They don't know how it works either, and we're all struggling with trying to understand it. We've done a lot of testing. But in any case, every time you sort of make some step or leap somewhere, suddenly there's not fewer questions, but more questions. So be careful and get yourself in trouble. If you look at square grid, which is a classic space room generator, this is our solution to that. But one thing I didn't mention, if you look at this carefully, you'll see that some struts, there's a pointer here, fantastic. It's going to play music, I think. If you look at this strut, you'll notice that it has 3 tabs. Am I saying that right? Yeah. I'm at such a weird angle. This one has 3, this one has 4, that one has 4. These are equivalent to the shape-coded elements of the modeling system, so that even though the node isn't there, the symmetry properties that existed in that modeling system are incorporated into this. In fact, I don't think that we would have been able to understand how to do this had we not gone through that other step first. That is to understand these geometric systems from the point of view of the symmetry, because it predicts all of the locations of these tabs. And then you get into, once you get to that and you get to here, you have tabs wherever you need them. You then discover that you can vary this infinitely and make any kind of geometry you want. This is equilateral triangles in the plane. I don't know whether you know the space-frame jargon, but the members in the plane of the space-frame are called the chords, and the diagonals are usually referred to as the web members, the spatial diagonals. That has 9 members meeting. Here's a system which has 10 members meeting, which is based on isosceles triangles. Normally, if that was, you would use that particular configuration on a 45-degree slope, and what we discovered was that by changing various dimensional parameters, length ratios, angles, and relations with tab to the node center and other things, you can vary it so that you can do all kinds of things that we didn't originally know were possible. For example, this is a project that we finished recently in Denver, which is a Skylight, and it's 100 feet, from that point down to there. There's 2 of them. It's built on the ground, but it sits at a 45-degree slope. I mean, a 35-degree slope, which was what the architect needed. And the thing was built on the ground, lifted in position, and then flown into the buildings. Details, there we go. And it gets covered with glass, and you see some of the mullions there, those rectangles. And this was much more interesting than flying kites. And it took a total of 45 minutes to take that from the ground and set it right down into place. And you can see it coming down into this space. It's now, oh Jesus, I just got some slide back today of the thing with the glazing I didn't even look at yet. I should put them in here. Anyway, it's setting down in here, and you can see the kind of nodeless connection, which looks almost flower-like at the connections. The glazing mullions. There's a footing, which is an expansion joint. There's extra tabs put on to hold the aluminum extrusions for the glazing. There are other glazing systems too. Right now, we don't have any of our own systems, although we're working on some adaptations of neoprene systems. An art shot. Now, the question is, how do you get all these parts made? And this is, now we're in our factory. What happened? Anyway, another art shot, right? The first thing happens is that the tubes get, the tubing we don't make. Obviously, you get that from a steel mill, and you buy lots of it at a time, and it comes in all kinds of diameters. We make systems from, say, 7/8 inch diameter to 4.5 inches, 2-foot long struts to 12-foot long struts. The system is within limits independent of scale. I don't think we could make a 2-mile diameter strut or something. It's kind of strange, but so the tubing comes in, you cut it to length, the high tolerances, then you close the end of it. There's a machine that welds those things on, and then it goes, you can see it so close. There's that, those shower curtains in the background are filter out the arc from the welding, and that's where the tube ends get welded. There's cutoff saws here. This was taken a number of months ago. This is our factory, which is an interesting building. It's 30,000 square feet. You haven't been there, have you, Glenn? It's now absolutely packed. You can hardly walk through the place. Might give you some idea what's happening. The welding. There's a guy welding there. That's a machine made out of a couple of lathes that makes prototype struts. We can dial in any angle or any position. We need to make a few struts for testing configuration. That's that's good to see that. That's the welding machine that I was talking about. The computer's on the left, although it was barely started, and now it's almost finished. It doesn't look anything like that. But The reason you need that machine, that automatic welding machine, is to build structures like this, which is a 2-acre space frame that we're building right now. The irony of this lecture is that the lecture was prepared for another presentation a month or so ago when we thought we were going to make this with an automatic machine. We're now hand welding. This thing has 30,000 struts in it. What you're looking at is a scale model. There's a 90-foot span between this pointer again. From this point here to that other cluster is where the columns are. There's 21 columns supporting 2 acres in a series of 91-foot spans. The module is a 5.7-foot strut. What this is a photovoltaic solar collector support structure and shade canopy over a parking lot at Jeddah International Airport in Saudi Arabia. And the geometry, we're looking from the south, you see the little photovoltaic collector panels. The colors are the Saudi flag colors. That got changed. This was the consulting architect on this project is a guy named Richard Schoen who teaches at UCLA. I hope that's all right if I mention UCLA. And what we did is we designed a structure that would provide the proper display angle as an integrated part of the space frame for the collectors. And from the east, it's you can see that it's a corrugated structure. So the actual corrugations provide stiffening in the direction of the span and that sort of thing. And it has sheet metal shade panels. The panel colors are now, what we discovered is when you go over to Saudi, everything is dirt color, because if it isn't dirt when you start, it becomes dirt because there's lots of dirt there that blows around. And so the color chip was a piece of masking tape pressed into the ground and brought back, and we're matching that in the polyester finish. That's an elevation view. That those columns have changed a little bit, but the principle is the same. The problem with the space frame is that when you have localized high concentrated loads in columns, you want to diffuse them into the structure as gently as possible so that you can maintain a high degree of standardization in the parts. And the form of the structure really kind of expresses the distribution of loads within it. Another detail. So that's just a scale model. We have, well, here, we're back to the factory. We recently did a test program, which you see happening on the right, which you see again here. And that's Terry Rainey. I don't know whether anybody knows him. He graduated from SCI-Arc. Working on that. But what this is a piece out of that Jeddah space frame structure, which is spanning 27 feet. And we do computer structural analysis of these things using finite element technology, and you get the loads in every member in the structure. You get all the deflections. It tells you whether the members are loaded in tension and compression. The computer model doesn't really give you the complete answer on the behavior of the joints and so forth, and you need to go through certain levels of verification. So we finally decided to the only way we could deal with this was to set up our own whole testing program and instrumentation and so forth. So we have various kinds of presses. We can destruct test individual struts. We can put loads on the ends of struts. We can do all kinds of things. In this case, we built a structure which, if you can see, there's a hydraulic cylinder that's bolted into the floor right in the center of that thing. It's attached to an I-beam, which then has two pipes that go up to two nodes at the midpoint. And the center top cord member would be the heaviest loaded member. We did a structural analysis, computer analysis of this, so we knew what the loads were. There's another view of it. You can see that beam focus isn't very good. And you can see the cylinder there bolted into the floor in the beam. All that cable coming around goes to strain gauges. There's 32 strain gauges in there. And then there's a XY plotter that plots deflection against load. And what we needed to do for the Jeddah, to verify behavior for Jeddah, was to put about a 20,000 pound pull on that cylinder. But our calculations and the computer model showed, and our testing showed, that in order to actually destruct, to go past the elastic limits of the structure, and to actually buckle or break or rupture something, we needed to get to about 32,000 pounds there, which would put about 41,000 pounds in the upper cord member. So we're humming along. The thing is really cooking. Its behavior is unbelievable. I mean, it's absolutely, there's about 25 people here watching this thing. And, well, there's a little sensor there that measures deflection adjacent to the cylinder. Here's the XY recorder, which plots the deflection against load. Whoop, I have to stop a minute. That was the punchline. What happens is that we're looking at this thing, and we're sort of, in order to read the strain gauges, you have to load it in 2,000-pound increments. So we went up to about 20,000 pounds, and everything is fine, and no creaking or anything. And people are starting to take bets, and so we keep going, and we get up to 24, and the tension is increasing. 26,000. We get to 28,000 pounds, and we're thinking, Jesus, is it going to make it? Theoretically, it couldn't go beyond 32,000 pounds. The whole thing is going to fold up at that point. But at 28,000 pounds, everything is fine. There's no permanent. There's some elastic deflections, but there's no permanent deformations anywhere. And so I said to Terry, "Okay, let's go another 2,000 pounds." And he tweaks the lever, and there's an incredible rumble, and the structure jumps about 4 inches off the ground. And what it did is it pulled the floor. It destroyed the floor, and the structure was still in perfect original condition. And so there was this great applause, and then I broke up into hysterical laughter. We've declared this day a national holiday. So we said, well, we can't stop here. So it took us about 2 weeks to repair the floor. You have to wait for the concrete to cure. We dug a big hole and went back into it. And we found that that's a detail of the connection. This is an unfinished thing. Now this is the new mounting into the floor. And there we are about to do it again. And what happened was that we got it back together. We went on up. We got up to 30,000 pounds. Everything's holding. We got to 31,500 pounds, and the top cord buckled exactly where it was supposed to buckle. So it was kind of the whole thing was a legendary experience, and it meant that the behavior of the thing was absolutely beyond anything we had dreamed, because it meant everything was in perfect balance. You can see the bent strut there. I mean, it's really pretty minor. We're going to replace that strut and repeat the test, because the guys that bought the strain gauges now have a new computer, and they want to do the thing all again without charging us anything. So we're going to do that. And that's the extent of the. I don't remember whether you remember that first slide, but the bolt is a little bit. This is called a single shear connection, and the bolt is tweaked just a little bit. So even after the thing has buckled, which is technically a failure mode, you can't get any more data out of the recording instrument. At that point, it's still, the structure didn't fall down. I mean, the things are, if the space frame is designed right, it's very, very safe. These failures that you read about are not real sophisticated space frames. That's another subject I won't. This is a project that we're doing. By the way, there are SCI-Arc graduates involved in both the JETA project and very heavily involved in this American Airlines thing, including one who's in the audience tonight, Greg Davis. And I don't think anybody else is here. Anybody else here? This is American Airlines corporate headquarters, which we did with William Pereira and Associates. Arthur Golding was the architect. There, and it's a public access corridor and public space for a complex of office buildings, which is part of the new corporate headquarters being built in Dallas. And the JETA structure has 30,000 struts. This has 24,000. So we've got about 50,000, over 50,000 struts to build in the next few months. And I don't have any. Oh, that was the study model of that structure. That's the dump of the computer run on American Airlines. There's 24,000 struts. We looked at, I think, 27 or 28 load cases, which comes out to about 700,000 bits of information, pieces of information, in terms of what the highest loads are in the struts and that sort of thing. There's some summaries of that, but it's slightly mind-boggling. We're now in the, see what's next. There's a model of the American Airlines structure in our shop. This building was originally, had small offices in the front and was the factory in the back, and we thought we were going to move to that other building that you saw and found that we needed all the room here. So this is being converted to offices, and since you're now in the back, you might as well see the front door. No, we're not there yet. I'm out of sequence. This is the front. So as you come in and you're walking through the thing here, and we have all these models around because you have to, this is Terry, You have to build models of everything. There's no way you can make sense out of these things unless you go through a model stage. We've learned to draw them. We can do some pretty nifty drawings, and of course you can do them on the computers. But that was the person on the left there is from SCI-Arc. And these are, on that wall are a series of generic models, generic space frame types, of which are about 9 or 10, and then from there you can go into infinite variations. We have little drafting tables, which are space frames too. That's Carol, my administrative assistant, and this is my office here. And this is my kids. Those weird-looking things, those truncated octahedra in those packings, was some leftover inventory from one of our toy products. We overbought, so we now use them for all kinds of other space dividers and stuff. I should ship a box of them down here. You guys can have fun. So everybody's kind of made their own. It's Diane Gould. Giannis, who went to SCI-Arc, and Mick on American Airlines. That's the hat rack. And this is Giannis's birthday party. Lunch, typical lunch, and back to the structures. This is a study model of a sawtooth roof. Very interested in the possible use of these in terms of energy control and sunlight control and that sort of thing. So incorporating a sawtooth into the space frame in an integrated way enables some structural efficiencies to come out of the sawtooth as well. And this is just a variable density space frame, part of a proposal that we did. By varying the density of the geometry, you can control the distribution of forces and minimize the differences in member wall thicknesses and bolt diameters and things. This is a proposal for Herman Miller, a furniture company that we did. This one we kind of acted as architects. This is our corporate headquarters in Zeeland, Michigan, and it's a 100,000 square foot, it's a 1 million square foot facility, which includes the corporate headquarters. When you get there, when you arrive there in Zeeland, Michigan, you can't find the front door. You don't know where to go. If you find it in the wintertime and open it, all the cold air blows in. So they wanted a kind of an entry thing that would solve some of those problems, and this was the proposal we did. It was a totally retrofit thing. It didn't go ahead because after we did it, they hired another architecture firm to do the master planning, and they changed around the functions of the building. But this is just a study model, fairly detailed, using the model system. The nodes, most of them the spokes are removed with something we call a node picker. These are shade panels. This is a project we're doing for Huddle, Jim Hull, Huddle store in Westwood. There's one in Orange County. He has a piece of property off the Newport Freeway. This is a very strange triangular-shaped lot, and this building is designed in response to both sunlight control, adaptation, trying to get the greatest amount of floor area out of this weird-shaped lot. Display windows on the freeway side, and there's 3 wind turbines housed within that sort of wing on the back end there. And we've done some wind tunnel studies, and I don't know whether it's going to work. I think it's supposed to work. The function of the wind is to accelerate the airspeed, the ambient airspeed, so that you get enough speed to drive those turbines. But the whole thing is going to have the floor and out of the space frame and clad in aluminum. This is if you add a fourth member to that modeling system, which ends up being a trapezoid in shape, if you remain consistent with the symmetry principles, you end up with dome capability. This is not a geodesic dome system. The geometry is totally different. With a geodesic dome, you end up minimizing the differences in edge length, but you also maximize the number of parts, particularly in large structures, and you have no adaptation possible within that. This is a system of 3 different member lengths, or 4, which can be infinitely varied. This is it slides in backwards. It's a school proposal. That model is 75 years old. No, it's not that old. Pretty old. 12 years old. Indoors. Moving into smaller scale, this is an exhibit structure. We really are selling these things in 3 market areas. Most of it is in architecture, and that's where most of the attention is focused. but we do some exhibit work and some parks recreation. That's a little trade show. This is a bigger trade show for Hitachi. Which can the focus be improved, or is it a lost cause? Or are my eyes going bad? It sure looks out of focus. This was a trade show at the Consumer Electronics Show in Chicago. It gets used every 6 months. Chicago, Las Vegas, Chicago, Las Vegas. The two-story structure has a stairway going up to the space frame, which you see here. We're just finishing a project in Tampa which incorporates such a stairway, and we'll have a stairway in the Huddle building, permanent stairway. And it sort of comes out of the space frame. The railing, the hand railing, is part of the space frame. And there's a stair truss that supports the two stairs and so forth, leading to conference rooms upstairs. Just some details. This was not, other than the fact that it did have floor loads, not a large span situation, but it does show the kind of range of possibilities. These are not equal length. There's two member lengths in this structure, which is very typical, corresponding to the triangular and square branches of the modeling system. That's the redo, to say, of Hitachi, which was triple the size of the original one, and that's back in Chicago at McCormick Place. This is a little shade canopy in Los Coyotes Park, which is in Orange County. It's actually a bandstand, and there's the band. The shade canopy. Those are sheet steel panels which we make. There's a funny story about this thing. The space frame is made to very high tolerances. We're telling people that we are at about a plus or minus 10 thousandths. We're trying to get better than that on the hole-to-hole distance on a strut over, say, 4 or 5 feet, which is a very high tolerance, unheard of in the building industry. So this structure, which is on a 4-foot module, is very accurately made, and if you measured from one end to the other, the overall length is probably within a 1/16 of an inch. So it's very high tolerance, and we did these drawings. And we take the goddamn thing down to the site, and the columns, which are put in there, are 6 inches off the center line, and they're trying to blame us. And it's your fault that the columns, that the structure doesn't fit the columns. And puzzle about it. So those cans that you see on the top are to disguise the fact that the thing doesn't match the column. Usually I just say that they're to keep rats and kids out of the roof, or ratty kids or something. This is a typical footing which comes through. Since there's no node, you can do all kinds of interesting things to solve those problems. And that's a piece of that structure in the back of our place, which was built. I think it's 8 by 40 feet, and it's lifted on a 40-foot flatbed truck, which has its own convenient crane. Normally we don't do the erection, but we have done some details of that. This is a very big scale structure. It's a 12-foot module with a 4.5-inch diameter member, Beale Air Force Base up in the Sacramento area. It's a dining hall roof. And there's some very high loads in it because there's a concrete roof on it, and there's some big cantilevers. And the architect, we didn't participate in the design of this originally, so we had to make what was not really a very good design in the first place work. On this one, we have a mixture of round and rectangular branches on the roof cords to support the corrugated metal deck. So worked out pretty well. And we go from that to very small scale systems. This is actually the first prototype of this nodeless multi-hinge connection system on a playground, which you see here in Aspen a couple of years ago. And some details of that. And this is another playground at the same park where that bandstand structure was, which is very large. These are rhombic dodecahedron, in case you didn't know. There's some sitting out in your parking lot. And it's a stylized dinosaur because Los Coyotes Park was a fossil find second only to La Brea tar pits in the area, and the slide is the tail and so forth. And now it's landscape. By the way, this is about what it looks like in Jeddah, except there's no hills that I saw, and none of that stuff in the background. And this is now landscape, and you can see the shade canopy in the left background. And finally, every feature has to have a cartoon short to go with it. This is one other system that we make, or the introduction to that. If you consider the picture on the left, on your left, that's a classic chemist model of the ball and stick model of a diamond structure. The balls are carbon atoms and the sticks are the bonds. If you leave the balls off and have the sticks become hollow tubular members, and then enlarge your diameter, you get the picture in the middle. If you continue that process until the inside and outside spaces are exactly the same size, you get the picture on the right. That becomes a kind of a molecular environment of the diamond crystal. It's clear that that chemists and crystallographers don't believe that atoms or crystals are hard balls joined by rigid rods. It's really more like the picture on the right. If you extended that infinitely, you end up with a, by the way, important point here is that at the point where the spaces are equal in size, the volume is minimized again. It's like the soap bubble, and those curves really are minimal surfaces. If you extended that infinitely, you entered one set of tunnels and I entered the other, we would never meet. We would never find each other. If it was transparent, we could see each other. We would have identical spatial experiences. We would see one half of infinity. It would be infinite, but it would still be half of whatever the other part of it was. If you took that molecular environment and enlarged it 8 billion times, not millions, but billion times, you would have our other product, which we call the curved space system, which is a giant diamond molecule that electron scale kids climb through. And you see them here having a jolly good time. Those components are injection molded polycarbonate, or so-called lexan. This is a shell structure. There's no supporting framework. It's an interesting combination of extraordinary. It's not a membrane either. It's a rigid structure. Some people think this is kind of elastic and inflatable or something. The linear members are splices that hold the shell pieces together. Each piece is about 2 square feet. There's some flat hexagons which are both open and closed. And this kid's sliding down. And what's interesting is you get inside of it, and it's like a slalom. You have to change direction every 28 inches in elevation change, so you sort of zoom down. So it's safe. At least that's what we tell our customers. And we've had, that one's in Irvine, which is adapted to a hill. We had one in San Diego, still there, which people have tried to destroy with fire and cherry bombs and all kinds of stuff. It's pretty tough material. In this particular one, we discovered late one evening, we were down there working on a project, that these young guys in their 20s invented a game they play called bubbling. And I think they were sober. What they do is they would start at one end and they conduct time trials against a stopwatch, and they would pick a predetermined route, which usually would go up into the thing, and they would go through there just as fast as they could, sort of leaping and jumping and sort of coming out the other end and try to get the fastest time through that. Apparently they do this 2 or 3 times a week, so they seemed to survive that. And that was a better destructive test than we had been able to envision at that point. It's the same structure. They're curious to me because as you sort of walk around them, they look like different. The gestalt is the same, but the overall shape changes quite radically. And one of the ideas that has always interested me is the extent to which you can build random or asymmetric overall configurations out of highly symmetric subunits. And I'm convinced that the better understanding you have of the properties of symmetry, the more likely it is you're going to be able to successfully create something that's adaptive in a very unsymmetrical way, which is often what happens in nature. This is the same one. This was the first installation we did, which is the Brooklyn Children's Museum in 1975. And this is a protein molecule made out of the same parts that kids go through. This is a science museum. And there were 3 structures there. This is a large diamond again. And finally, that's the wrong slide. It's the right slide, but it's the wrong slide of the right slide, if you know what I mean. That's one in Japan, which is the world's largest. It has, well, to give you an idea of relative size, the one in Irvine that was on the hill has 17 cells or 17 atoms or 17 volumes, whatever you want to call it. This one has, I think it was 94. Yeah, it's 94. It's 50 feet in one direction, about 25 in another, and 20 feet high. And there are a couple of sort of amusing anecdotes about this. First of all, I went over to Japan. This is at Hakone, which is a open air. It's south of Tokyo in the mountains near Mount Fuji, and it's a very beautiful area. And there's a open air sculpture museum there, which has an extraordinary collection of Western 20th century sculpture. You name it, and it's there. And the benefactor of the museum wanted to have, apparently the Japanese adults bring their kids to this place, and so he wanted to have some objects there, an object that would not embarrass this great sculpture, but which would provide some participation for the kids. So he thought this thing would do it, and so I went over there and looked at the site and sort of worked out a configuration and proposal. God, they're tough negotiators, I'll tell you. And we worked out a price, but we didn't have the time. I didn't have much of a staff at that point. Didn't have the time or really the inclination to want to stay there for 3 weeks supervising this. Not that I wouldn't like to spend 3 weeks in Japan, but I would be doing other things. So I was going to do that. So the agreement was that they would send the assistant curator, who was a very nice Japanese guy trained in kind of classical architectural history, to come to our place in the U.S. and be trained. And the guy was terrific. But he spoke almost no English, so he came over, and for about 2.5 days we spent most of the time going to jazz joints and museums, and put him to work in the back with some tools and sent him away with some drawings and models and other things, and shipped the thing. And we didn't hear anything, and the next thing I get these 2 beautiful scrapbooks that document almost every minute of the whole process of installing this thing, from building the footings, and it was absolutely incredible. And it was really a kind of a neat experience. They since have ordered another one, which we just shipped, which is smaller but more expensive since inflation is. We also learned how to negotiate with them a little bit. Final story then about this was the thing that they were almost compulsively concerned about was they didn't want the surface to get scratched. And in the U.S., these things are typically in unsupervised parks, and what happens is that they, the sand is drug in and they get scuffed and scratched and so forth. But it's always fairly uniform, and it follows the pattern of traffic, and it really doesn't hurt the play value, nor does it really dramatically affect the appearance. I mean, if you're 25 feet away, you don't even notice it. But nonetheless, I wanted to be absolutely certain that there was no scratching. So I thought about this for a few minutes, and I said, well, since you have a tradition of removing your shoes when entering sacred environments in your country, if you simply consider this to be a sacred environment, I think the problem may be solved. And I don't know whether that's how it came down, but if you go there, there's little shoes that are lined up by the door, and the white socks keep it beautifully polished, so it's, it worked out pretty well. All I can say is it was there for about 1.5 years, 2 years, and they ordered another one. So a reorder in the toy business, if you got a reorder, that was the ultimate achievement. So I guess we're okay on it. We have one in Caracas, and we have 3 in Southern California. We're building one in Palos Verdes that's quite large. I think it's 34 cells or 37 cells or something like that. And some in San Francisco. We don't do much marketing on this, but somehow people seem to get interested. They always say, Jesus Christ, that thing is expensive, and then they end up ordering an expensive one. I've never been able to understand that. But anyway, that's the end of the slideshow. I think I'm exhausted. I would be glad to answer any questions. I've asked too many questions in my life already. I'll be glad to answer any questions, or try to answer any questions you may have. Why don't you turn on the lights, and let's go from there. The drive-in must have there's more people here than when I started. The movie must have let out somewhere else, and people thought this was some other kind of event or something. No lights in this place? Aha. Hello? Somebody. Well, God, that's a tough question. And the future plans are to try to figure out how to get through the next 2 months. No, that's a good question. Having become a committed manufacturer, or a manufacturer about to be committed, I think is really probably more appropriate. To this kind of technology, the philosophical answer to I'll give you 2 answers. I'll try to give you a philosophical answer, and then I'll give you more of a technical answer. Philosophical answer is that what our plans are to follow a path which enables us to successively test the limits of this kind of a strategy in more diverse, more difficult, more whatever kinds of situations, more comprehensive, more whatever it is. What that means as a practical matter is that what we're committed to is going from the space frame to totally integrated systems. For example, one crucial thing, and Glenn is familiar with this because we came into it on the green machine, is that space frames now are used where the only practical fireproofing solution are sprinklers. So you have to work within some code constraints that allow you to use sprinklers. In the case of the green machine, we're talking about running water through the system, and that is an acceptable solution. And it works on fairly large scale. At least it seems to check out on a cost-effective basis on large scale systems. If you get to a 4 or 5 foot module, then it's hopeless. So we are, and you don't solve the problem with, spraying junk all over it or encapsulating it in asbestos sheeting. So we are committed, among other things, to solving that problem. Glazing, cladding, we'll be working on housing, integrated kit housing systems based on this. Now, I'm not here to defend that as an idea. Somebody said, Jesus, I don't think the space frame makes any sense for housing. I don't care whether you think that or not. I'm just saying that we're going to build some prototypes and find out whether they work before we try to sell them to anybody. So generally, we're kind of committed to evolving and developing the natural course of technological development that will expand the use, or let me put it this way, to try to find out where the limits of the use of these kinds of systems are. Jesus, that was a long-winded answer. But I think does that answer your question? I don't have a exact 5-year plan. I'm basically a very pragmatic person in that sense. So I need to, you need to sort of complete certain feedback loops to find out where you're going. But as we evolve the automation of the design process, which we're also working on now, computer-aided design techniques and other things, we will begin to devote more and more time directly to product development and less to doing the projects, which get done with fewer man hours. And what I can say is that there's no other space frame company, certainly in the U.S., and I don't think anywhere in the world, that is committed to this. They are building space frames, and they've got a lot of business, and most of them, and that's really fine with them, but they're not interested in it. I think we're unique in that sense, that we want to find out where. So you had a question? The same question? Yeah.
I found it interesting that you terminated your lecture with
Uh-huh.
my question
Is there hidden meaning? Is there hidden? I know what it's on the hint.
It's to do with aesthetics and the love of sexuality that developed versus like the space frame has certain parts and triangulation and so on, and more structurally oriented. You have a callback for that pure polyhedral project. Starts to go at, I think, tie into small scale elements like maybe dwelling with respect to goal easier space framing is going on in the neighborhood.
Yeah, I mean, I have some. Well, the two or three answers. The first one is that there is no hidden meaning to having it last. That was a matter of convenience. But the question that you asked I don't have a simple answer to it, but I think that you have to think about a number of issues. Probably the most important one to me that comes to mind has to do with what the relationship of one's perception of these systems are and the size of the increment that you're using out of which you build them. I believe, for example, that I could build, I'll start out as a defense of the articulated sort of space frame strategy. I could build you a space frame that you thought was the other system if my increment was fine enough, and I could argue that the clear plastic thing is there's a space frame hidden in there. It's just a very fine increment, and as you And one of the interesting questions is, what is the relationship? I mean, an interesting theoretical question is, how do you, I mean, you could, I get into the word, into the idea of diversity, but you could substitute that word for sensuality. You'd say, how fine an increment, I mean, my question would be, how fine an increment do I need to get a significant amount of diversity out of the standardized system? Or you could say, how fine an increment do I need to get satisfying sensuality out of the thing? And so at some point, those things cross over. And when I developed these things, I really didn't ever think of them as separate systems. So at the scale that they have manifested themselves, that curved space thing is absolutely universal appeal. I mean, you're absolutely right about that. And maybe all we've come to at this point is that when you're what we are doing with this geometry, in a sense, is we are in effect solutions looking for problems. In other words, we come at it with a certain kit of parts, or a certain genre, or a certain, I guess, a kind of rubric, which manifests itself in a physical way, which becomes, I mean, so what you have to do is you have to say, if you are ostensibly a solution looking for a problem, then you get into this whole process of natural selection. What is the fit? What is appropriate? What is an appropriate fit for this particular rubric or kit of parts? And I guess all I could say now is that the only fit that we found available to us at this moment was the playground application of those curved things. We have not, in my book I show drawings of, I don't know if you've ever seen those, but there's drawings of multi-story buildings made out of, instead of an inch and a half or a foot and a half edge length, it's a 15-foot edge length on those things in the reinforced concrete, and they sort of fit together, and that's one particular approach. But do I think that that's too pretentious an answer? No. I agree. Which do I like?
Yeah, when you look at the soap bubble or you look at the spacecraft, I mean, when you look at the sports or something, you told me like you like fluorescence too, or things like that. But there's a certain sensuality, there's this curvature, the smoothness, the directness.
Yeah.
You know what I mean?
Yeah, I'm hip. I can dig it. I can.
I just would assume that that you have a preference, whether it has application right now or not is something
I have problems with that. I mean, I love the curved space for all the reasons you said, but I also love the other thing, and I don't. I mean, I like tall, skinny girls and fat, short. I mean, it's. There's no one, I mean, I don't have any one sort of, a lot of things are beautiful to me, and for different reasons at different moments, and I have a hard time pulling those out and saying that one is, I really don't believe that the curved space is more beautiful than the space frame. To me it isn't. I mean, it has certain properties that the space frame doesn't have that are quite beautiful, and I don't look at the space frame and try to find in it what's in the other one and vice versa, but I see. I'm just a practical bastard. I mean,
space frame makes more money.
Well, I think that well, actually, I don't know whether, I think at the moment it's probably less profitable on a single unit by unit basis, but, and it's an interesting thing. The curved space is absolutely unique. There is no, if we get specified in a park, we get specified. This whole issue of competitive bidding is out the window. I mean, nobody, it's patented and the whole schmear. If we're doing a space frame, we're out there and there are 3 bidders and all this bullshit that goes with that. And if I was, you think if I was a shrewd businessman, I would sort of go for the thing that was, except that it's a small market and so forth. But that isn't really what it's about. What it's about is that this is what I was trying to say earlier, is that the space frame is the solution to more problems than is the curved space right now. And it has a certain market, except it is a generic solution. The curved space is not. It's theoretically a generic solution, but it isn't in the consciousness of the profession. Yeah.
Well, in terms of your
Yeah.
Really, these are just a lot of little nodes together.
Right.
Without the connection.
That's right.
You know, whether these go from, satellite to satellite in space, all of a sudden draws all of these tiny things down together.
Yeah, right.
Thing happening right after. I think that's kind of what a lot of people see.
Yeah.
So once you get the whole apart, now we have to do this one satellite.
Yeah. Yeah. I think, I mean, if, I don't want to make light of your question. I don't think it's a, but I would say that I can't answer the question, which do I think is more beautiful, because, and I answered that. If you allowed me to be pretentious again for a few minutes, I would say that the problem with the curved space, in a practical sense, is that it is highly unadaptive compared to the space frame. I mean, it's more like a geodesic dome. It is what it is. It happens to be very complex and periodic in some variation. So you're forcing the function into the shape. And if you're interested in entertaining kids and you want to teach them about molecular structures, that's an appropriate thing. But
I think you're doing too much physically
mm-hmm.
predominantly sort of be applied to other applications. They probably even could be applied to the space frame.
Yeah.
An attitude sort of soft. That was my basis.
Well, I do have in my book a whole thing about how to make space frames map those curves, and all you're doing is, a geodesic dome is just a triangulated map of a sphere, and you can do that. There are various optimum ways to map triangulation over that curvature, and that gets to be pretty interesting. You can even integrate the two systems. Yeah, it's the sort of basic strategy that is in fact common to both the space frame and those shell structures that we pursued is that the fundamental stability of the structure is given by the geometry. So when you have that situation within certain limits, the structural viability really is independent of scale. You may get a little one or a big one. You do have, local bending problems or whatever it is, but the basic stress distribution mode in the shell structures is virtually the same as it is in the triangulated structures, in that it's always in the plane. It's not, there really isn't any bending other than the local bending of somebody jumping on it or something like that. So you get it bigger, you just have to make sure it's thick enough. And that particular, you would have some material limitations presumably, but see, most of the time you see those curved surfaces are used as membranes, as tensile structures, whether it's a fry-auto tent or some other kind of thing, and we're not using it that way. We're saying that those are in effect equivalent to strut elements or shell elements that are capable of reducing compression loads, and so in that sense it works differently. Any other questions? Yeah. God, not another one.
Why are natural structures or let's say cars or computers that are very more beautiful? Because they go through the same framework as
I never said that and probably never would, because that wasn't the reason for doing it. I mean, I'm not sure what you mean. I think you mean, what do you mean by classical? I mean, give me a couple of examples. What you mean? Right. Mm-hmm. Mm-hmm. Mhm.
natural beauty is not like intellectual.
Mhm.
But they still both your work and the work of the Greek level are beautiful because we look at them and we have a successful where we kind of like just keep it beautiful. I'm just wondering like
Well, you're saying they're both beautiful. I guess. Are you saying?
for the same reason. And I don't know why. Because we are about nature and expression.
Yeah.
And I don't know how can you say like nature expression like, you know, why is that like including other parts of the mind? And what's the date? What's the exact date?
I like.
What's your reason for making it beautiful?
Okay, that's. Oh God, that's heavy.
It's the postmodern question.
I'm hip. I'm hip. I'm hip.
It has nothing to do with postmodern. That's the same.
Well, let me answer him. I mean, I can't answer him, but let me see if I can be pretentious again. Forgot the question. Pardon me? Well, there's lots of difficulties in the question, obviously, and one of them is, you know, you have to define what you mean by beauty, I suppose. I mean, I know what I wanted to say. What I wanted to tell you was another anecdote, which was that the title of the book was used to be when I was before it got published. There was a last-minute change in the title, very subtle, but what you said, the way you responded to the title, suggests that it may have been a mistake, which was the book was called "Structure in Nature as a Strategy for Design," and the editor at the last minute says, "I think that it would be more forceful to say structure in nature is a strategy for design." The difference there is that if you say, when you say is a strategy for design, it's a more messianic kind of title than as a strategy. You're sort of saying that that's the only strategy for design. And I think that all I can, the only, the humble answer to the question is that I don't, I'm not saying that this is the only way, even though I, you know, do this work with great passion and conviction, and I am not interested in anything else. I also don't say that that's the only way to do things. I'm not into postmodernism, but obviously, but so I'm not. In one sense, I'm not competent to answer your question. Because I'm not doing this out of an aesthetic mandate. In the sense of is it beautiful or not beautiful in some kind of, oh God, this is impossible. You see what I'm getting at? I'm not to me aesthetics and beauty and stuff are not how things look or how they appear. That's part of it. And you know, a Greek temple involves some sort of formalism, some intellectual constructs that, I mean, some people probably think Greek temples are ugly, who are not dumb people, you know. I'm not personally passionate about Greek temples. I respect them and I understand the, you know, and I would certainly go see them and would admire them and all the rest of it, but I don't get, I mean, if I went to, I've never been to Athens. If I went there, I'm sure that I would get very excited about it. But so I guess what I'm trying to say is that the mandate is not a self-conscious aesthetic objective, is all I'm saying, for me. So it's very hard for me to even respond to the question.
Well, I think the dad is like kind of like I want to know like I come to the idea that both the like architecture based on perception, whether it's from a natural or intellectual point of view,
right,
are pretty much the same thing. What I'm wondering is like, how does your architecture relate to its society, and how it has that fit within like and the use of production and the architecture being produced and the corporations that produce these. Like what kind of architecture?
Well, what kind of architecture it is remains to be seen. I mean, I don't think. I mean, some people will say, God, it's high-tech architecture. I don't know what that means. I've been doing this before anybody ever said the word high-tech. I mean, that's just another fad as far as I'm concerned. I'm not into fads, but what I believe is that when you work on a problem, let's look at some simple problem, like if you looked at an Eames chair, which most people, let's say, you know Eames furniture? I mean, I know some of you do. If you took the classic Eames plywood chair, not the lounger, but the humble little thing made out of 2 pieces of plywood, and you look at that thing and you think, well, Jesus, that's really beautiful. And you could say that Eames invented an aesthetic with that chair, and a lot of people respond that way and feel that way. When I first became familiar with that, which was some years ago, when I looked at that chair, what I responded to was the coherence of it. And I said, well, what's really going on there? And I said, if you're designing a chair, I used to design chairs. If you're designing a chair, you can be very rational about it. You can get into the ergonomics and stuff, and you have to do that. If you don't, I think you're irresponsible. But you always come to a point where there are certain aspects of the problem that you seem to have to be arbitrary about. And it enters into this sort of realm of aesthetic license, if you will. And what I feel, what I believe is that what the objective there is yes, you have to be seemingly arbitrary, or to put it another way, you have to be intuitive about it. You can't put it in the computer and get the exact answer that you may want. What you're doing is you're making a sort of leap to a higher plane of rationality, maybe, but the objective there is to answer the question from the point of view, what is the most appropriate solution, not what is the most beautiful. Because if you say what is the most beautiful, most of the time you're going to be, that answer to that question is going to be governed by fad, by very temporal kinds of considerations. And that's my belief. So the idea is to my mind, is to minimize the arbitrariness by seeking some sort of sense of appropriateness. That's pretty vague, I know, but I think that my feeling, what to me the lesson from natural structure is to get a better feeling for what's appropriate. And nature is not arbitrary in the way it organizes the structure. So you want to try to understand, I'm very biased towards design as a response to performance criteria. And in that sense, if you say, what does it have to do with society? It has to do with, saving energy or whatever all this stuff is, which is now popular. But people said to me, 15 years ago when I started doing this, why do you want to do that? Why do you want to save material in a structure? And I said, what? Just seemed like a reasonable thing to do.
But like an Eames chair, not everybody can make an Eames chair. It requires a lot of technology.
Absolutely. It also took somebody like Eames who had an extraordinary sense of what was appropriate. Sometimes. I've been called a fascist. I mean, I really have been called a fascist. I don't know. You're gonna get blunt now. I think that those are absolutely gigantic leaps of logic. I mean, I can't. That's really moving fast through. I think that the problem. Let me make one final thing because we're in this philosophical mode. I think that one of the great problems in Western culture and culture as a whole is what a great limitation to true understanding is what I think of as a kind of a binary logic if you will, a polemic or a dialectic. I mean, what it does is it says, if this is true, that can't possibly be true. And I think that's just bullshit. I mean, I think that the problem is that you need to integrate, that things are not mutually exclusive. I think when you try to understand the world from that point of view, you're going to miss whole levels of understanding. I think that you gotta, you know, if you think something's beautiful and it doesn't work, I'm telling you that it's not beautiful. And if you think it, you know, I mean, I have great trouble with, you know, whether it's some simple human situation, and the truth is always some sort of middle, integrated kind of perception. And I think that this, you know, binary, I mean, it's sort of Aristotelian, evolution of Aristotelian kind of attitudes, I think is, I'm not putting Aristotle down, but I mean, I have trouble with the right brain, left brain. I mean, it's a very fad kind of thing right now. I mean, I refuse to believe that my brain is split into two halves. I mean, I think of it as one of those curved space labyrinths with these two integrated, sort of mutually penetrating things, and I can't, I mean, somebody says one is intuitive and one is rational, whatever. It's probably true, but I have a very hard time with that because I think it's, when I taught in an art, when I was around scientists, I thought I was a mad artist, and I just have terrible problems with those kinds of ways of thinking about the world. Anyway, I rambled on enough. Any other questions? Yeah, steel. Most of the time, steel. We work sometimes with aluminum. Steel is an incredible material. It's from a sort of cost to performance point of view, very hard to beat. Aluminum space frame is frequently twice as expensive in terms of dollar cost. You only use it if absolute light minimum weight is an issue, which it usually isn't. They're already very light in steel. Right. You can. You don't. Sometimes you change it. The question is, I think the question was, if you vary the density in the space frame, you also change the fundamental geometry. The answer is yes and no, depending on what the needs are. You can do it either way. It's easier to keep the geometry the same, but just cut the strut in half and subdivide it more in a finer increment. But you can also change the angles and do whatever. I mean, with our system, that's easy to do. It's not easy to do with fixed node kind of connection system. So it gets very expensive. There's no real cost penalty in our system for doing that. Right. Mm-hmm. Well, there is that particular system. The parts themselves are fixed. You can't vary them unless you make another die and make another part. There's a larger family of parts but there's a very small number of different part types. But you can, with that particular kit of parts, make more than one shaped labyrinth, say, or cellular array. It's just that the other ones are not safe for kids to climb through because they have different geometries. I mean, you can make a cubic grid out of those same parts, for example, but if you do that, there's no way to orient it so that the kids aren't in danger of falling great distances. So I figured. Yeah, well, you can do that, but again, you have the same problem. I can tell you that no kid who's ever played it came to me and said, geez, this is really neat, but if you had some different size cell shapes in here, this would be more fun. I mean, so there's been no reason to do that. There's no way that, we studied in scale models all, I mean, I have a sort of a storage place full of, I built models of all, literally almost every possible way you could put those things together, and there are a lot of varieties, and you can combine different cells and do what you're talking about. And you can do that theoretically, and you can build the models, but there was no useful or practical way to do that for this particular application. Yeah, you can do that, definitely for architectural applications. But it's still very limited compared to what you can do. The increments are volumetric increments as opposed to structural increments, so that the increment is relatively close to the size of the volume, so you have a limited capability for adaptation. Yeah, that's what I'm talking about. I mean, the geometry goes to hell. You can do it if you want a totally arbitrary supporting network, but then you have a non-system and it becomes unmanageable. You could build it, but you're talking about large money and probably incoherence. You probably would get so damn confused trying to deal with it. Anything is possible. It is? I'm not sure I said that. Yeah. You're on shaky ground. No, it's not. Those are injection molded. Yeah. Polycarbonate. Lexan, have you ever? We did some prototypes, vacuum form prototypes. Oh, really? Did I represent that story? Was it a reasonably accurate representation of the story? Fantastic! I've never met one of you. Actually, I wasn't there. Some of my employees were down there. I didn't actually see it firsthand. I didn't seem disruptive to explain that during the lecture. Any other questions? This is fun. Yeah. Well, right now, if on the basic unistrut modulus system, if the project is of adequate size, we would be competitive. Probably a little less, in fact. But when you get down to small projects, at the moment we're not, because we have to. At the moment, the way we're organized, every project is a custom project, so we have a lot of engineering costs and stuff. That will change during the next year, because we are in the process of doing a whole series of generic studies on that, so that even on very small structures we become very competitive. We are, when you move beyond the basic unistrut, where you have any other kind of problem that has any complexity, we become extraordinarily competitive. On the American Airlines project, for example, we were 30%, 33% less than anybody else who could build it. Our bid was $1 million installed, and the other two systems are $1.5 million. And that's Dallas, Fort Worth. It's near the airport. It varies, but the price runs from about, I don't know where we are now, about $7 to $12, $13, $14, $15 a square foot, depending on the size of the project, the geometry, the density of the structure, the scale of the member. No, that's just the frame. It really depends what you're going to do. Plywood, I don't know what plywood costs. To give you a little bit of perspective on that question, that Denver project that I showed you that's glazed, the space frame was $23,000. The aluminum extrusions for the glazing was $17,000, and the glass, which is double pane, insulated glass, dark tint, was $27,000. The glass alone was more than the space frame. So what happens is that surface costs a lot of money no matter what you're going to build. A Luca bond, which is that nice aluminum laminate, is about $6 a square foot or more, and so on. So it's hard to find cheap. Plywood is a damn good material. I mean, it's really hard to beat it, sort of cost performance
Thank you, Peter, for your...
Thanks.
Put up a good fight there.
I want to ask you something about what he was saying about the definition of the difference between classical beauty and natural beauty, because to me it seems like back then and as we go back, they seem to be more sensitive to nature. I had a hard time with that definition
I'll
of
talk about it.
being definitive and those
Let me give you, I'll give you one. I think the only way I can think to answer that is one story about Plato. There's five polyhedrons, probably not called the common solid. Plato goes
none have been known afterwards, right?
well, no, those are the regular five, yeah. Right, and he was so excited about these things that he associated them with the elements, with their fire and water. And if you look at the analogies or analogs that he made, I think the tetrahedron was fire, oxygen is water, the oxygen is air, and he made the cube the earth. And if you thought about those, and the dodecahedron was the whole universe, and if you thought about the physical characteristics and properties of those elements, call them, and you built as structure those various polyhedrons, you probably wouldn't come to that conclusion. You probably would not make the cube earth. You'd probably make the cube fire or water, unstable and very primitive and ground. And it's clear that Plato's attitude about this was really a kind of visual, intellectual. He was not, and in fact the Greeks were not really very well connected to the physical. It was very cerebral, very intellectual. And you get a kind of aesthetic that comes out of that. It wasn't that they were trying to create an aesthetic, but it was their sort of cosmic view, their sensibilities about the universe. And as science emerges in history, the connection to the real behavior in the physical world becomes more accurate and so forth, so that you then have a shift, maybe in what is thought to be beautiful even, I don't know. So that if you look at the classical thing in that context, you admire it and it makes sense and it was done with great conviction and all those things that make the world wonderful. But it's a different reality today than it was then. Does that make any sense?
Oh, yeah.
No.
I had taken the first design course I ever taken, the basic design one. I got that book later, but it was the sequence that you follow very much.
Where does he teach? Where did he teach?
Well, first he was in North Carolina. He taught at Washington University in St. And now he's teaching at the American University of Beirut. That's where I came before. Very much, very much.
How are we going to pick them?
Where do you live in LA? There's one in Carson. The best one to see probably is the one in Irvine that I showed you. And I can, well, it's easy to get them. University Culver Drive. If you're going down the capacity, you're going to come to Culver Drive.
No. Friday.
Things up to
Go about 3/4 of an hour.
It's going to take that much
There's a park there
to
called.
do that, so probably Saturday afternoon they start. This is
Yeah.